All right, I'm back. I'm just going to get a little bit of water, and I'm going to take a few minutes just to answer any questions anyone has. I don't know whether anyone is watching or anyone's going to be watching by the time I'm back, but if you have any questions, type them in the chat. Otherwise, I will get back to work. So I don't think anyone's here, or no one's asking any questions at the very least. So I'm working through problem set 8 right now, and I'm getting into some hiccups because I'm a little rusty with my multivariable calculus, in particular with spherical coordinates. I'm dropping factors, and it's not working out exactly as I wanted to. So I could kind of just just grind through it as I have been doing on some of the problems that I haven't understood everything completely. But this is sort of a basic concept, so I don't think it's going to get cleared up. Like they're not explaining in any of the notes. So I don't think that just ramming it through is going to be the solution here. So what I'm going to do is just spend a few minutes looking around for some explanations here. I went through my textbook, but I'm remembering that I didn't actually use this textbook for doing when I did it in the MIT challenge. I just used the lectures in the class. So what I think I'm going to do is I'm going to just switch over right now to this view. And let's go here. I think this will work. And I'm just going to look around, see if I can't find anything. Maybe I'll just move this over a little bit. So let's go to 1802 MIT OCW. All right. Do we have lecture notes? That would be a lot faster than watching video lectures. This may... Polar coordinates, do we have triple integral surface integrals in 3D space? Spherical coordinate surface area, vector fields. Okay, I think we want this here. I might have to look at divergence and curl again. Some of these ideas are a little bit fuzzy, so let's just look at it. So spherical coordinates, rho, distance to origin, phi, angle down from z-axis, theta, same as in cylindrical coordinates. Diagram drawn in space and picture of 2D slice by vertical. We've got integrals here. I don't know whether this is actually partial derivatives. Do I have derivatives in this space? Because this is what I understood from this is what I understood from the this makes sense for the integral. So, let's go back to our problems here. So when I was doing these problems, I was getting some, see, I guess my questions, I'll write it down over here so I can kind of phrase it out. So I guess my question is that we have, for, maybe I'll just switch over here if I'm going to be doing, so we have row, is that how you do row? I think that's, row looks like this, yeah, row, data, let me just do it with the pen so I can make it a little clearer here. We want, which is the order we normally do it. Go around this. So this is going to be 2 pi, and this is going to be from negative pi to pi, right? I think we go 0 to pi by 2. Go back to our notes here. Oh, what are you doing, Milk? Oh my God, this cat. There, you happy? What are you doing, eh? All right. This one goes from, was it 0 to pi, or is it negative pi by 2 to pi by 2? We're going from 0 all the way to pi. From 0 up to infinity. And then we're going from, oh, okay. All right, down. Down. Hey. All right, hey. Hey. Okay, down you go. Down you go. And then this one, I think we want to go from 0 to pi. 0 to pi, and our theta go completely around. But now our what's called infinitesimal volume is not a cube. This is x and y. Yeah. How can I draw this a bit better? Let's draw it like In particular, it is wider it's actually not like this. We want so what are we doing here? We have this disk. Some infinitesimal so where was the? I think I put this somewhere else. Oh. Ba, 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 ba. This Academy one I was looking at. Let's see. So we have R and I want to look at more information on this because if we're doing this derivative, you know what, I might watch a little bit of this lecture here. Where do we have? I don't have it download, so I can't watch it faster, but do we have an interactive transcript? Maybe I
The
can.
following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Maybe I just want to look at the transcript. Okay, here we go. Oh, shells. Centric. I think we can do so we want to get it from here. Flow direction. Is it not loading?
Okay, so last week we've learned how to do triple integrals in rectangular and cylindrical coordinates. Questions about that? No, from the horizontal axis. But the idea in here is latitude, in the sense that it measures how far north or south you are. The only difference is in geography, latitude is 0 on the equator and becomes, something north, something south, depending on how far you move from the equator. Here you measure latitude starting from the North Pole, which is at 0, increasing all the way to the South Pole, which is at pi. And theta, you can think of as longitude, which measures how far you are east or west. So the Greenwich meridian would be here, now all around the z-axis, but I'm just drawing a slice for one of these vertical half planes, fixing the value of theta. Then R, of course, is a polar coordinate seen from the point of view of the xy plane. But here it looks more like you have rectangular coordinates again. And so the idea of spherical coordinates is you're going to do polar coordinates again in the RZ plane. Okay, so if I have a point in here, then rho will be the distance from the origin. And phi will be the angle, except it's measured from the positive z-axis, not from the horizontal axis. But the idea in here, see, is, well, I'm going to put that between quotes because I'm not sure how correct that is, but in a way, you can think of this as polar coordinates in the RZ plane. So in particular, that's the key to understanding how to switch between spherical coordinates and cylindrical coordinates, and then all the way to XYZ if you want. Right?
I don't know how helpful this is going to be. Oh, unfortunately, this interactive transcript doesn't seem to be working, so I can't just find the parts that I want. I think I'm drawing the right picture here for this. d rho is going to be an infinitesimal addition to the length. D phi is going to be infinitesimal d phi. And then the theta is going to be, so sort of think for this angle here. So this one, and then yield by but we were trying to figure out for integration what's going on here. Let's go back to our original problem here. What were we doing wrong? What was I doing wrong? So hold on a sec. Let me go back to this problem. I think I can answer it now. So we had L squared operator is equal to minus h bar. And then this is going to be y10, which is equal to root 3 over 4 pi root 3 over 4 pi. What was the? Oh, this is the answer here. We want cosine theta. What is this equal to? Um, d theta sine of theta d theta So we first apply this operator once. We'll go on sine squared theta. All right. So what does this brackets mean? This is in the other bracket. It just means we apply this twice, so we get minus h bar sine theta. So this gets turned into sine squared theta. Or derivative respect to phi is going to give us what? Well, this is going to just cancel, I think. Put a question mark there. And then if we do this again, derivative of sine squared theta, we can just move the 3 bar. Integral of sine squared is going to be what? Well, that's going to be the derivative of this is going to be sine hi Aryan. Sine chain rule here. We've got sine theta squared. That's going to be what? Sine x sine x. 2 sine x cosine x. Let me check. 2 cosine x. So this is these cancel. And we're left with minus h bar a over 4 pi cosine theta h bar. And LZ is equal to minus h bar. Which is also 0 for those. So if we have it for let's do the y y1 state. This is the only one where we're going to have a phi dependence. Well, we just drop down the I here. So this is just I11, right? Is that what we found? H bar. Oh, right, H bar. IH bar. So the value is equal to. Oh, yeah. This cancels. It's just H bar. So I don't think we have any problems with this. I think it's only integration that we're going to have to be careful about. Otherwise, I don't think it matters. Because these seem to be normal. I think the problem I had was I didn't look at this properly. So I don't think the problem is actually spherical coordinates. All right, C, construct 2 minus 41. Yikes. What the heck's that going to be? We do a racing operator, loading operator. It only goes between the states. How would we construct this really large spherical harmonic? I mean, do I have to just look at the pattern? Is it going to be... let's see. We're going to have... This is going to be what? Some root. The cosines are odd. This is an even one. I think we take the sum to get the odd or even. I would say we're going to have cosine theta because this is odd overall. And then it's going to be e to the minus I. And we're going to have 41. What's the pattern? What would the pattern be? Well, it's just a normalization constant. So I don't know why that's changing though. Just gonna put n. I have no idea. All right. From class, we know that lifting operator here, h bar e to the plus or minus I. Theta cotangent. minus h bar. I do not remember this from the class at all. E I-42. All right, this is fine. Oh, right. Okay. Oh, that's useful. Okay. Theta 42. I-42. Sine 41. Was this in the notes? Let me just see whether we covered this when we did spherical harmonics. Oh, look, I even wrote nothing need to understand better. There, I'm reaching from the past telling me that I don't know this stuff. All right, well, I think we know where we're going to be doing some Feynman techniques later. So let's just keep moving. All right. Angular momentum and uncertainty. The commutator relations derived in problem 3 imply an important set of uncertainty relations amongst the angular momenta. Consider a particle in a normalized eigenstate of L squared and Lz. Psi is proportional to YLM, and psi is normalized. So I think the thing I'm not certain about this is I guess what they're saying is that you can't you can only have angular momentum in one direction. I think that's true of classical mechanics too, though. Use the operators. Plus. So how do we show this? So what were those operators? What were the L plus or minus operators? How do we use the lowering operator here? What would be the trick here to use the lowering operator or raising operator? So L plus L minus would be Lx plus ILY, Lx minus ILY into Lx squared. Right. Plus Ly squared. Don't quite know what that gives us. I guess is the idea that like this can only no, 0, 1. Does that show that our expectation value is? Thanks, Rodrigo. I feel like I'm missing something. How are we getting these L1s? L plus L1. Psi. And same argument for that. Okay. All right, let's try B. Show that Ly squared equals Lx squared is equal to minus h bar over 2 L plus 1 minus m squared. So this is going to proceed in the same way as this last one, I guess. is the mean raising and lowering of raising in? Probably, right? So we want to have set ly squared l squared. And we have this is Lx. I think that we need Lz. Lz we can just leave in. L plus L minus I2. Which can just be this, and then this could be minus. YLM. So these are going to give 0 because of orthogonality. This one is going to give our L squared eigenval. And maybe minus our Lz eigenval squared. So what were our, I think we calculated those before, didn't we? Yeah, I think we just have to go with that stuff that they have given us here. So this is going to be what? H bar squared L plus 1 minus H bar M squared was H bar squared L plus 1 minus M squared. I lost a factor of 2 somewhere. Oh, right. There we go. Yeah. Okay. So C. C, using your results, verify the first uncertainty relation above. Can the uncertainty in any two components of L ever vanish simultaneously? So, all this is going to be and the square root of this. Did I lose a square here? No. So this is equal to h bar over 2. And what is the L expectation value of LZ is going to be equal to h bar m h bar m. Yeah, equal h bar m. So we take the square root of this and multiply it together, and we get the same thing. And then we have well, we're not getting rid of the m there. Why would that be the LZ expectation? So I'm not entirely comfortable with why this becomes, let's put this. Why is that? We know, so we know it can't disappear. All right. Read this one. These are just, oh, okay. Hold on a sec. greater than h over 2. Okay. So that is problem set 8. Yeah, why not? Let's get going on problem set 9. I'm just going to take a quick break to sharpen my pencils. They're getting pretty dull. I need to buy a new eraser soon. All the erasers and my pencils are getting all rubbed out. So now we're on to the Coulomb potential. So let's do problem set 9. Okay. Let psi and LM R denote the properly normalized energy eigenfunctions of the Coulomb potential with principal quantum number n and angular momentum quantum numbers L and M. Consider an electron in the state so we have phi R is equal to C. So C, we need to get this all normalizes. So C is going to be what? 1 over root 1 squared. Maybe not 1 squared. What am I looking at here? So when we multiply these things all out, we need to get them to square. 16. Uh, 26, 27. Root 3, root 3. Over. Yeah, root 27 is 1 over 3 root 3. My brain's getting a bit fuzzy right now. I think that's right. Because these are just superposition of linear states. So these things, when they square, they all have to add up to this. B, expectation value of energy. So expectation value of energy is going to be, what is... One 1/27th E. Oh, this is too much. It's 16. What am I doing? This is 8. 8 over 27 E 2 negative 1. Now what are those? Let's open up our clue. What do we have? Is there anything for clue? Let's see it. So let's go over to is there E naught? Do we know what our E naught is? $127. And 24. What am I doing? Oh my god. Oh boy. Basic math. 1/25 this, and 24/25 E naught. Is 2 squared is 4. 16. So expectation value of E is, yeah, it's this. But I don't know what the E naught is. Oh, here we have it here. So it's equal to no, that was just our dimensional analysis. Can we figure out what the E naught is going to be? I don't remember what the E naught was. Okay, I don't know what E naught is, but I'm going to leave it like that form right now. C. Let's flip this over so I have it open already. C. What is the expectation value of L squared? This is going to be total angular momentum squared. Well, we have 2 states. So it's going to be what, 1/25. Don't remember the units of this. This should be. This is going to be. Wait, this is going to be times 0. There's no angular momentum there, and then this other one is going to be the same. It's 24/25 times. What's the unit of this expectation? I think it's h bar squared. What did we do here? We got this eigenvalue here. L squared. That's from the last problem set. I don't know what the units are going to be. All right, and then D is going to be LZ. It's going to again be 25th times 0. 16 to the 25th times 0. So I don't know what those basic units are. E, well, this is just going to be this whole thing. Is equal to R times in the IT. What is this? What is our energy operator here? Okay, let's look at some of these answers. Okay. After some correction, that's right. Find the expectation of you. Okay. E1 plus E2. So what do we have here? Yeah, this I got this. Ah, this is not E naught. This is the first excited state. So this is why is it divided by 51? So we have 1/5, 1 to the 25, and then we have this E1 plus what was that? I think 4n squared. N is 1. This is E naught divided by 4. How the heck do we have 24 E2? This makes sense. Why is this 51? Not even a multiple of these ones. So we have yeah, it should just be equal to where do you get the 51 from? Yeah, I have no idea where they're getting this 51 from. There's a 1 in 25 chance that they'll get this, and a 1 in 25 chance that they'll get 24 and 25 chance. So I'll get that. All right. Let me just jot it down on this. So we have 1 in 25 times E1. This is going to be 1, 16 E2 plus 8 E2. And that's going to give us 1/25 E1 This has to be a mistake. They just gave C up here, so how do you... I don't know. I must be missing something, 'cause this looks like it's wrong. Okay, I think I got that right. Expectation of L squared. This one I didn't know the units. Okay. Uh, 16. So it's going to be 16 times 2h bar squared 8 6 h bar squared. All right, and then this other one is going to give us just H. MH, I guess. So it's just minus H. Minus H bar. Okay. And this one. Let's see. E to the minus I ENT over H bar. It's minus E1. Oh, this is 1. E1 T H bar plus 4 psi 210 R e to the minus I 2T over H bar minus, this is an I for an I here. 2 psi 2 minus 1 R times E to the minus I. Where minus 13.6 for hydrogen. All right. Let's where does a weakly bound electron live? Question 2. A. Show that R the expectation value in spherical coordinates, I guess. Do we have the close one? See, I jotted some stuff down here, but maximum orbital angular momentum. I wrote some things down here, but I don't see. don't see any of the actual functional form here. I don't know whether that was in the class or not. So we have I'm going to get the answers for these going forward just because I think it'll help me understand it better. But I'm probably going to have to review this class. Which class is this? Coulomb potential with class lecture 17. Do I want to keep going? Yeah, I'm going to look at them. Okay. Let me write this down. Yeah, see, I don't think I had these. I mean, were we supposed to derive them somewhere? And minus L minus 1. Yeah, I definitely don't remember. They maybe didn't give them in the class. Maybe this is a recitation thing. Do we have something here? I don't think so. Okay. Times L 2L plus 1 Y M I. Yikes. Okay, that's a bit of a mess here. Laguerre polynomials. L K P Laguerre. Yeah, I don't remember this Laguerre polynomials. The case where L is equal to n minus 1. Minus 1. This 1, 0. Equals 1. Okay, so this, let's see if I can just solve this now that I have this. So now that I have this, we know that it's gonna be this times r times this. I'm actually just going to be his triple integral here. This is norm squared, right? This is norm squared. I'll just put this here. Oh, this is an awful mess. I don't have any idea what I'm supposed to do here for this. Well, these are all constants, so this can all come out. And then this is equal to 1, I think. So then all we're doing is really integrating over e to the negative 2r naught. N minus 2. So we should be able to integrate by parts on this. But I think we should first integrate over sine so we're going to 2n r naught cubed 1 over 2n minus 1. And we want, this is going to be r squared sine, which is, I don't think we don't drop I have to do this step by step, don't I? Cosine at these bounds should just give us no. We're valuing this one 0 to 2 pi. So just give an overall factor of 1, I think. Wow. We can take these to be two n minus 2. If we integrate by parts, what do we get? So that's uv minus u prime D, right? Let me just look up integration by parts real quick. Just so I can remind myself. Yeah, okay. So if we do integration by parts, what can we change this to? We'll go over n rho naught cubed 1 over 2n minus 1 factorial. And we're going to have, well, let's put this here. Which one do I want to make u? All right, I'm going to just check to see if I'm even on the right track here. Okay, did that. 0 to infinity r cubed. We lost an r. Oh, right. Because we added the r in. All right. I don't understand how we get this just is equal to. So they're saying this is equal to 2n r naught minus 4. I mean, they must have used some kind of algebraic solver for that. I don't think that they actually solved that analytically because that's just a nasty thing to do by hand. Then you get this. We'll cancel this. This will just be minus 1. And what do we have? We have nRO 2 times 1 over 2n. n plus 1/2 there. Oh, 2n plus 1 minus 1, 2n plus 1 factorial. That means we're going to remove this is just going to be n RO 2 then we have 1 over then we have 2n plus 1 2n and then these cancel and we have equals to n r naught. Wow. Okay. A lot of work to get to that, though. You know what? I think that's probably a good time to call it for today. So I'm just going to switch off here. Oh, it's getting dark out. I didn't even notice. So where I'm at, I'm working now on problem set 9. I think I'm on which question? I'm on question 2 of 5. I've kind of just started that. So I've just started problem set 9. There's a possibility that I'll get done the first pass of all the problem sets by tomorrow. At this point, there's a lot of stuff that still needs to be really dug in there. So I think after this first pass is done, I'm going to do a full analysis of every single problem set and write down every single concept that I didn't get right the first time or concept that I still don't understand, even knowing what I know now. There's still a few questions that I haven't done yet. In the earlier problem sets, I think there was one or two that involved an applet, 1 or 2 that involved a video. So I'm going to skip over those. I will come through them again at another time, but I think what I want to do is finish all the problem sets, get a full list of everything that isn't solid, isn't like I really understand this, go through them each in detail so that I do understand them. I'm feeling right now like I did a little bit for spherical coordinates, and I think if I felt like I had a little bit more time, I would have been more patient with that. But because I'm kind of pushing it right now, I'm trying to get through the problem sets. I didn't want to take too much of a detour if it wasn't helping with these problem sets. But once I get all the problem sets done, then it's going to be more a question of, can I go through and try to fix all of those weak points? I don't know whether I'm going to do the problem sets again for a second pass. I might do some of the questions that I got really badly. I might do a second pass of them. So I might mark those down when I'm doing my analysis to figure out which questions were the hardest. Definitely going through all of them a second time is probably going to be too time consuming, but maybe doing the ones that I did worst are going to be worthwhile, especially once I figure out what I did wrong for those ones. But like a lot of them have quite involved math. I think we're getting into ones where they're expecting you to use Mathematica to solve it. I'm not familiar with Mathematica. I didn't really want to invest in learning it for this class. So especially because I really doubt it's going to be an issue for final exam type problems. And it's definitely not an issue for intuition type stuff. I think this is kind of important if you're going to become a physicist, but not something I really want to invest a lot of time in. So I think what I'm going to do is try to finish. I might be able to finish it tomorrow. Let me just see how many question problems that 10 has. Yeah, it's pretty long. It's 8 long questions. So I mean, if I'm maybe Thursday I'll be finished everything. And then going through all the problems, it should be fairly easy to just go through with what I've written down here. I've put most of the solutions in notes here. I can make a list of all the concepts that I didn't have down tight. I mean, some of them have been repaired in the meantime. So some of them I've gotten better at just through more practice of having gone through the problem sets. But I think that will give me a good first pass of which ones which ones I needed to look at the answers to get, and then also which ones, even after looking at the answers, I'm still kind of confused about. So I'll make a note of those, and then I'm going to probably spend the rest of the time doing Feynman techniques working on that. I might look at some of the exams too, not the ones that I have solutions for, but just some of the exams, and I might practice on those. I think as we're reaching kind of nearing the end state, I should be able to feel good about my own sort of self-feedback for the exams. If I can do the exam and I really need to know what the right answer was, I'm probably not ready yet. So I can probably use that as kind of a rough feedback guide for how I'm doing. At some point, we're probably going to run out of time. So I don't know how far I'm going to get. This is a hard class, and basically there's a lot of concepts that need to be built on. And I'm going to go as far as I can in this month. And then if I think that I need more work, I'm just going to sort of decide as I'm reaching the end of the month what I want to do going forward. So I already mentioned that I don't like to plan too much for those sorts of eventualities, because as soon as you tell yourself, oh, well, I'll give myself 3 or 4 months to do it, then you stop working so hard. So I'm still going to go according to plan until the last minute if I have to make some kind of adjustment of what I'm going to do. But I'm also stating that, like, for the record, I'm not entirely clear that I can get up to speed on this in the amount of time. We'll just have to see. I definitely can get further. I'm just not sure whether I can get to the point where I'd like to be, which is where it's trivial, it's obvious. I'm not sure whether I can get to that point in this 1 month period of time. But we'll see how far I can get. I'm going to keep working at it. I'm going to be back at it. I'm going to try to keep the same schedule tomorrow. I might have to do a little bit of work tomorrow that's not related to the project. So I might have to take a longer break at lunchtime to work on that. But otherwise, I'm going to try to do as much as I can. So I will, with that, I will see you